Hey guys, welcome to Containers and Mission Critical Applications session. My name is Yoni. I'm a Chief Enterprise Architect in Vanguard. And today we're going to talk about our journey into containers. First, a little bit of introduction about Vanguard. It's one of the world's largest investment companies. And we started operation in 1975, the year when I was born. Vanguard is strategically located between Wall Street and US East 1 data center in Malvern, PA. We have multiple lines of business, and we are currently managing a little bit over $5 trillion in funds. So today we're going to talk about our container journey, talk about the reference architecture that we put together and we have implemented. Talk about data protection, identity and access management. Talk about infrastructure protection using Aqua. Some reliability conversation that ECS offers, ECS the service. And then finally, we're going to close with some next steps and cost optimization advices, kind of like lessons learned and where our journey will take us, and if you follow, probably you as well. So when we started on this journey, we kind of, it was a year ago, we had an existing, I want to call it legacy container orchestration system using a third-party provider. We had it for about 5 years. We ran it on-prem, and when we decided to go to public cloud, we also decided to use the same system because we knew how to use it. Over the years, we kind of understood that the system is fairly complex for us to manage operationally, and we wanted certain things to change. So some of the design principles that we followed in this new implementation is the next system or stack that we want to deploy or implement has to be fully distributed. It has to enable DevSecOps, although if you heard the keynotes today, you probably know it's not a thing anymore. It's just ops. It has to be backwards compatible with that legacy system that we are replacing. We need to make sure that the people that want to migrate to the new stack or system don't have to do too much with their application code in order to switch over. It has to be fully automated and fully automationable, secure by default, and cost-effective. Although when you see the stack, you might think that it's not, but it's more cost-effective than what we have today, and that was the goal. It's more cost-effective than what we have today. So then, this is our stack, and I'm going to talk a little bit about this in detail. A little bit of primer, though, for ECS, for those of you. By the way, anybody here uses ECS? Okay, good. ECS with Fargate? Great. So I'm just going to mention it briefly, just so we know, when I say certain things, what exactly do I mean? Because it's a little confusing. So ECS is Elastic Container Service. There are three main components of ECS: Elastic ECS Cluster, ECS Service, not to be confused with ECS the service, and then ECS Tasks. So the first component, the cluster. When you deploy ECS with EC2 instances that run your compute, ECS Cluster plays a role of grouping those EC2 instances that run your container nodes, your ECS tasks. When you switch to Fargate, all of a sudden ECS Cluster loses its function. It becomes just a logical container. There's no association with EC2 instances anymore. So instead of, and again, when you deploy it with EC2s, you probably want as fewer ECS clusters and a fewer EC2 nodes to do as much density as possible. When you do it with Fargate, though, each Fargate node represents a task. So there's no density for you to worry about. You don't care how many clusters you deploy, and I think the soft limit on clusters per account is 2,000. And with our micro account strategy, that limit is not even in play. So we decided to deploy a microservice or an application ECS task and dedicate a cluster to it. So now there is a cluster per microservice. Of course, ECS service is something that groups a number of ECS tasks together, and it's within an ECS cluster. So each microservice running in this pattern has one ECS service. So it's like one-to-one mapping. And then the number of ECS tasks is decided by desired state. I'm going to talk a little bit about that. So we deploy a minimum of 2. We also wanted to create a single, if possible, CloudFormation template. By the way, we code everything in Troposphere or CloudFormation. So the code that I'm going to show you in the next couple of slides is in Troposphere. But if you know CloudFormation, you should be able to follow. So we wanted to create a single stack, highly parameterized, that will suit everybody's needs. There's going to be a lot of default values associated with it that you can override, but if you don't have to, the defaults are good enough for you. So by default, we're deploying 2 ECS tasks in 2 availability zones. Autoscaling is also autoscaling the service, the new AWS service that was rolled out, is also pre-configured in this template. And because we want to enable this DevSecOps mode, we also threw in an elastic load balancer, an application load balancer into the stack. So this CloudFormation template deploys an application load balancer, ECS cluster, ECS service, ECS tasks, and all the autoscaling bits. The rest of the components here, the endpoints, for example, they're already pre-existing in our VPC. So then the domain of this DevSecOps team, or ops team, is the compute and everything to do with their microservice. They can deploy as many of those as they want, independently of others. And when I say one of the design principles was distribution, we wanted this stack to be ISO-contained and distributed from one to another. We have multiple lines of businesses, as I mentioned before. Each line of business has its own AWS account. And sometimes contractually, institutional line of business cannot cross into retail line of business. So it's important for us that everybody lives in their line of businesses. When we have a shared cluster, or had a shared cluster before, it wasn't as easily accomplished. So that's another added benefit. ACM, AWS Certificate Management Service, allows us to rotate certificates easily. We install it on every application load balancer. And again, this also happens within the CloudFormation template, within the stack, within the deployment. And as long as the entry, the DNS entry for that name remains in DNS, in Route 53, that we use to validate ownership of those domains, AWS will automatically rotate the certificates for you, nothing you need to do for this. So that's another added benefit for us. We wanted to reduce our operational toll as much as possible, and that allowed us to do this. I'm not going to talk too much about state here, other than the compute nodes needed to be stateless. That's another design principles. They can come and go. They will be deployed in multiple availability zones. They can crash the application inside them, and the service will bring them up. We didn't want to maintain any states. So then the tasks will interact with services like DynamoDB using IAM roles. That's another added benefit of ECS tasks. You can attach a role to a specific task, and you do it through the service. So everything is on AWS Fargate. We didn't want to maintain any EC2 instances, not anymore. We have enough of those. And then let AWS take care of everything else. Okay, so let's talk about Fargate Security. Why Fargate? AWS announced it last year at reInvent. We started taking a hard look at it. It's implemented with Firecracker, or I think they're in the process of migrating every Fargate implementation into Firecracker. Firecracker is a micro VM which provides a host-based, hypervisor-based isolation for each task, for each ECS task that you're running. So there's no multi-tenancy to worry about. You're taking the shared responsibility model that AWS provides to the next level. Now, you're not even managing the compute nodes. They do it for you. So your domain of responsibility from security perspective shrinks even further. An ability to use task roles for native integration is tremendous. I don't think there is any other container orchestration system that exists today that allows you that level of granularity to have a task attached to an individual, to have a role attached to an individual task. So no operational overhead, no more hosts to maintain. Fargate and ECS both are 4 nines of availability SLA per region, and has a slew of certificates that are pertinent to us, like SOC 2. For other industries, maybe medical, there's HIPAA compliance and stuff like that, and a whole bunch of others. So it's pretty mature service, even though it's been introduced a year ago. So let's talk about data protection a little bit. We want to protect sensitive environment variables. If you used ECS before, if you inject environment variables, which is the only way to provide input into containers because they're immutable, anybody who has access to the console or can use any kind of describe command, they can see the clear text of each environment variable for each task definition for both key and value. So for protected or sensitive environment variables, it was important for us to secure those. We want to make sure there is an end-to-end encryption in motion. Certificates are issued by ACM. We talked about this before. We don't want to rotate certificates anymore. We don't want to be in this business. ACM allows us to do this, so we decided to do it with that. And whenever possible, we want to access all the data endpoints using AWS Hyperplane. So for whatever services are available, we're going to use AWS VPC endpoints, gateway or interface. So let's talk about how we accomplish sensitive environment variable encryption. So here is a logical description or logical visualization of IAM policy, or 2 policies rather. The encrypted value, we have like a master key. We can encrypt the value, or somebody can encrypt the value with this master key, and then the blob can be provided to the pipeline. The pipeline, or the agents of the pipeline, which are running on EC2 instances or Docker container down the line, have an instance profile or a task role, which allows it to decrypt whatever was encrypted with this master KMS key, and only encrypt, although this policy doesn't reflect it because of a shortage of space, only encrypt with key 2, which is a key for the individual task. So then the pipeline passes it to the CloudFormation template. The CloudFormation template has a custom resource. By the way, those of you who don't know, custom resource is a Lambda function that allows you to extend functionality of CloudFormation that doesn't exist there previously. So you can write a Lambda function to do that. That Lambda function can have a role, obviously with the policy. In our case, that role allows the custom resource, and it's own running within the scope of running CloudFormation stack deployment, right? So when it comes to the point where it has a blob that was passed as a parameter to the template, it decrypts it with one invocation of custom resource. It now has a clear text value of it. And then another invocation of that same custom resource, but with different parameters, it now encrypts it with key 2. It cannot decrypt with key 2, it only encrypts with key 2. And then the role with the policy of the task now running can decrypt anything that was encrypted with key 2. And now at runtime, when the workload, or the start script, if you will, of the container is running, it decrypts the value of the protected environment variable, and now it has a clear text in memory, and applications have access to it. Hopefully it wasn't too confusing. So how to pass environment variable into CloudFormation template as a parameter? AWS allows number of parameters to be passed. The most common one is string. There's no way for you to, unless you pass different parameters for key and for value, there's no way for you to pass key value in a single string as a pair. So we created this kind of pipe separated parameter type. And this regular expression basically allows us to specify key on the left and the value on the right of this pipe. Of course, if you have values with pipe, it kind of breaks the logic. In our use case, it works. But if you have pipe in your values or keys, I don't think so, then you need some other delimiter for this implementation, but this works with that. So remember previously I was talking to you about the encryption and decryption. So this is a section of CloudFormation template that does the decryption of the encrypted value with key 1. Again, it's troposphere code, but it reads just like CloudFormation, just more dense. Just a plug for troposphere. You can write it in Python. You could add comments. Now you have YAML, so you can do it still. But if you want to kind of have a more higher level programming for your CloudFormation templates, the output of it is, when you run and compile, the output is CloudFormation, but you implement it in Python. So the pertinent bit here is between the comment lines, right? So the encrypted text is the select one of the split by pipe of the value of the parameter that we've seen in the previous screen. The custom resource then, the VG encrypt string PYCR, takes this as well as some other parameters, the service token for the Lambda invocation. And then when it returns, the return value of it is clear text, but it lives within the context of the executed CloudFormation template, executed stack. And then the same custom resource with slightly different arguments just re-encrypts back, so that now we have an encrypted value with the key 2, so that the task role can decrypt it. Now, somebody with keen eyes could say, why not to use Secrets Manager for this? Why you complicate it so much? We're still working in standardizing Secrets Manager in Vanguard. We're very highly regulated industry, so it takes us some time to ingest products into our portfolio. This solution was available for us. It's a neat trick, so that's why I wanted to share it, but it's definitely not the most ideal way of getting at secret credentials. There are two other ways to do the same using AWS native services. I think SSM protected keys or something like that is one, and definitely Secrets Manager is another, which then by attaching a role to the task, you will allow a task to get something from an encrypted vault in Secrets Manager. Same idea. So here is another kind of a part of code which shows how we parse the environment variables. Remember, it's a key value separated by pipe, so select 0, split by pipe, and here we get the encrypted value of the encrypted with the key 2, and pass it as an ECS environment variable to the in a task definition. So let's talk about ACM a little bit. So ACM, now there is public and private. We actually looked at private because everything that we are doing in this stack is internally facing. Nothing has public IP address. There's a slew of components in a stack that ferries the traffic from the unprotected network into the internal network. So we looked at the private certificate ACM offering by AWS. It still lacked in capabilities from where we needed it to be. So what we ended up doing is, so we have Route 53 zone, private and public for every domain that we use. In order for you to validate a certificate with ACM, you need to create a record in a public zone, because that's how ACM, the service, is resolving, like coming from the internet, it wants to resolve the validation record that you created it correctly and you actually own the domain. But the host names for the load balancer, the application load balancers to which those certificates get attached afterwards, are actually living in a private zone because they're internally facing. So we kind of created this split brain architecture a little bit, and we use ACM Domain Validator, which is another custom resource that we wrote, which both requests the ACM certificate and then validates the ACM certificates and then waits for the service to validate. That can take a number of minutes. Again, all of this happens while the CloudFormation stack is being deployed. And you can pass alternative names. We support blue-green with our implementation, so we actually pre-wire the alternative names for the certificates into the certificate that gets issued to the application load balancer. So then the elevation so we have pre, current, and post. The pre is blue, if you will. Current is what's running in production, and post is something that if you want to roll back. All three of those names get pre-wired in the certificate. It gets attached to the application load balancer. And the elevation is something that you do in a pipeline. You promote from pre, and we just change DNS records. So pre becomes current, current becomes post, and then pre becomes available for you to deploy a new version. All of that happens throughout 53. But the certificate is ready to take any one of those requests, ACM, and the certificate itself doesn't need to change. So once the certificate is issued by the custom resource, we can then attach it to the application load balancer. By the way, not only application load balancer. I think recently they released a TLS-based for NLB. And if you worked enough with CloudFormation template, you know that from CloudFormation perspective, the difference between ALB and NLB is just the type. One of them is application, the other one is network. It all falls under the Elastic Load Balancing v2 CloudFormation APIs. Just something for you to know. So what are task roles? If you worked with EC2, you probably know what the instance profiles are. Task roles are very similar things. It's something that you attach to individual tasks within the service. You do it through the service, excuse me, because it runs identical tasks, just a number of times of them. So each task within the ECS service, the entity, has a task role that allows it to do certain things or access to specific resources. You can narrow the scope to the smallest denominator, like just the minimum necessary that you need to run, and it's application specific. So, remember the key example. Each microservice gets a KMS key. They're $1 a piece, and then whatever is encrypted for that application, only the tasks of that microservice or application can decrypt. Nobody else can. To attach a role to a task, it doesn't. Not every ECS service gets deployed with a role, but it's something that you pass in a parameter. We typically think about it. Let's say you have a microservice that uses DynamoDB. So you would deploy DynamoDB and a role for the ECS service that allows it to access that DynamoDB table in a way that this application is supposed to do. So a role and the policy would be deployed in the same stack. The output of that stack is going to be the role ARN. Then you take that role ARN, actually the pipeline does this in our use case, hopefully in yours as well, and then you pass it as a parameter to this stack, which deploys the ECS compute. And then the role, if it has, there's a condition, if it has the role task, the parameter, it gets attached to the ECS task definition. And now the tasks in this ECS service have the role attached to them, and the applications inside of them can do whatever that role allows to do. So let's talk about infrastructure protection. So I think there are a lot of talks in this conference about Docker security. For us, it's important that whatever tool we choose obviously can scan Docker images for vulnerabilities. It can then mark them or tag them as approved or unapproved, and we can define those criteria based on certain policies. It can protect the application at runtime. Everything becomes compromised, it's just a matter of time. So when a compromise occurs, how far the attacker can escalate the attack from a compromised container. We want to limit that blast radius, and whatever we chose for this as this tool would do something, would allow us to do that. Make sure that only tasks that have that runtime protection enabled can run in our environment. Alert and block the anomalies when they occur, alert the SOC, and obviously prevent access to compromise in a compromised scenario. So we looked at a few products on the market. Actually, when we looked, there was only one that supported Fargate. Most of the container security tools, even until today, that are out there, run themselves on a host in a privileged mode, and then they are able to interact with the containers from a container in privileged mode, and then do all kind of scanning and blocking. In Fargate, however, that's not an option. We don't own the hosts. AWS does. There's no way for us to deploy anything on a host. So then the solution that we chose need to be able to natively to support Fargate. We looked at a solution called Aqua. I think they're here somewhere in a booth. I'm pretty sure they're somewhere in the audience as well. So we were able to deploy Aqua, the whole stack, in the same architecture as every other microservice that we deploy in ECS Fargate, even with the same template. We had to change a little bit the type of load balancer. If you remember, I told you from the CloudFormation deployment, from a CloudFormation perspective, the difference between application load balancer and network load balancer is very small. So if you choose an option, for example, we have a protocol as one of the available parameters for the application. If you change the protocol from HTTPS to TLS or TCP, all of a sudden it becomes a network load balancer. We switch everything in a template. There are some other minor parameters that are specific to application load balancer. For example, only application load balancer can do layer 7 type health checks. Basically, be aware of the URI of the application. Obviously, NLB, which is a network type device, layer 3 cannot. But we deployed Aqua in this in the same template, actually 2 templates, because there are 2 components. One of them is using network load balancer. So the micro enforcer, which is all the way on the left, is actually a component which runs inside each one of our Docker containers. We prepackage it in the image that we make available for our developers. It's a small binary, probably 4 megs, and that is the component that makes sure that the image that is from which you're attempting to start a container is an approved one, using that policies, remember? And also, it protects the application runtime. So if there is any compromise or any kind of escalation the application is trying to do, the micro enforcer will protect it. It will block it from going any further. The micro enforcer, and I think this architecture is changing in the current version, but in the version that we still have deployed, it communicates with the Aqua gateways. Aqua gateways are deployed, also containers deployed in ECS Fargate, and it's using SSH over unspecified port. Again, it's running an ECS service, and then Postgres is the only place where Aqua Stack maintains state. It also has a UI component, which is also an API component, uses the same gateway, so it's deployed on the lower part of the stack using ALB this time, obviously with ACM. And the communication between the gateways and Aqua console doesn't happen directly. It happens through the database. So the moment the console updates something in a database, the gateways will get it as well. So for example, you want to change a policy. Once you commit, it changes the state in Postgres, running in RDS, obviously. And then the gateways get it as well, and the micro enforcers get it from the gateways. All of it is deployed in autoscaling. Images are stored in ECR, just with any other microservice in our ecosystem, and then ECR is accessible through VPC endpoint. One component here that you can see on the bottom, which is the only component which is not a container in our environment, is a fleet of EC2 instances that perform the scanning. Remember, in order for you to perform a scanning of an image, you need to be in privileged mode. Fargate doesn't allow you to do this, or at least not yet. So we have a fleet of EC2 instances which are disconnected from, you cannot connect to them. There is no SSH available to those instances. Those instances have an instance profile which allows them an interaction with ECR. They pull new images, and actually images that already exist, they rescan them periodically. I believe it's once a day, but as soon as new image appears in a ECR repository, which is pushed there by the pipeline, they will scan it within minutes, and then they communicate through the application load balancer, through API, to the console using a secure token in order to tag an image as approved or unapproved in a database, so that then micro enforcer will know whether you can spin that image from this, spin a container from this image, or you should not. So this is some of the examples of scans that are available from the Aqua console. Actually, you can notice that the smaller the base image type, the less vulnerabilities it has, which kind of makes sense. And there's a lot more advantages to having your image as small as possible. But the more moving parts, the less complicated the architecture. So here as well, the less packages it has, the less vulnerabilities it's most likely to have. So it's using a role-based kind of, repeating what I've said previously, it's using a role-based access to Docker image repositories in ECR. It pulls the images onto those EC2 instances that are the scanners, and they're kind of ephemeral as well, the scaling group. They scan the instances scan the images and mark them within the system of Aqua as approved and unapproved, from which the micro-enforcer then knows whether it can start the application or it shouldn't. They're periodically rescanned, and to make sure that whatever latest signatures Aqua adds, actually they use some third-party database that I think everybody else is using as well. There are a couple of those. So whenever this database gets updates with newer vulnerabilities, it's important to rescan your images to make sure that you're still compliant. So then the protection of the application at runtime, the micro-enforcer is going to be already deployed in the image because we prepackaged them in our images. And you can see here in the from, this is our internal images. We don't download images from the internet. We vet them, make sure they're sanitize them, and make sure they're secure before we make them available. We also deploy micro-enforcer, and we make sure we control the entry point. So at the entry point, it's important to make sure that micro-enforcer is the first argument before you launch anything else. And what it does, it creates a sort of envelope around the runtime within the container. And if, when something happens, which is the next slide, compromises will happen. We all know it. We're here in this conference because we know it. When the micro-enforcer is running in block mode, it actually can run in read-only or audit mode, so it will only notify you that a compromise occurred, but will not block it. Obviously, when you become comfortable with it, you want to switch it to block mode. And when it is in block mode, it will prevent the escalation. So here in this example, somebody is trying to run bin.ps from a compromised code, which is probably running in Python or Java or something like that, inside your container, and micro-enforcer blocked that execution. So even though the code inside the container is compromised, it wasn't able to escalate further. Now, that being said, running in Fargate, do you really care? It's not your host anyway, but you should, right? So SOC is alerted when malicious behavior is occurring, and we are blocking the compromised event. Let's talk about reliability, again, within the context of ECS Fargate in our stack. There are three types of parameters for the number of tasks in ECS. One is the minimum, the other one is the maximum, and the one which you care about the most is the desired. That's actually the term. Amazon ECS service will always keep the desired number of tasks running. So whatever happens, the desired number of tasks will be running. The desired number of tasks will change based on auto-scaling criteria, but ECS service will make sure the desired number of tasks is running. Now, if something happens inside the application, inside the container, application dies, for example, because that application obviously runs in foreground inside the container exits with it. ECS service, kind of like Kubernetes, runs those loops. It checks that there is always desired number of tasks, and then as soon as it detects that it's no longer running, it will spin them up. The health check from the URI perspective, or rather application layer server perspective, is actually done by application load balancer, or rather the task group within the application load balancer. Remember, network load balancer cannot do a layer 7 health check, but it can check if the container is listening on a specific port. So that also is done by the target group within ALB or NLB. And by default, in this template that we created, we use Amazon CloudWatch metrics, just the CPU one for now, to make sure that we scale up the number of desired tasks within the ECS service. So then, in this screenshot, you can see the ECS service, DKR service something CCT, Cloud Construction Team in CTO, in Vanguard. I killed this task on purpose just to make sure that the service spins it up. And you can see that desired count is 1, but the running count, desired count is 2, but the running count is 1. So the service spins up another instance, or another task in this example. The mapping between ECS service and target group is happening within the service. So you will create a relationship between the target group and the ECS, the service. In order for the load balancer, or rather the target group, has two types of targets. One of them is instance ID, the other one is IP. When you run in Fargate mode, obviously instance ID is not an option. The only option is available to use IP, but your tasks are ephemeral. They come and go. When they do, by the way, we're running in a VPC networking mode. When they do, they get a different IP address from within the VPC DHCP range. How does the application load balancer knows what the target is? You create this relationship, and that's how ECS service actually lets the target group know what the IP address of the task, so that it can begin doing its health check against it. And then the health check itself is specified in the target group of the application load balancer. In this case, because the protocol is HTTPS, you specify the path or the URI, the port, and those other things, like the healthy threshold, unhealthy threshold, the timeout, and the interval, are the minimum ones that the target group would allow you to do for the health check. Success code is always also configurable, but in our case, and I hope in everybody else's, 200 is success. I don't know of any other use case, but if you do, would be interesting to hear. And that's how application load balancer does health checking against ECS, the service. The auto-scaling is done within the service as well. So we still look in the screen of the service in ECS console. And we created, most aggressive scaling up and scaling down that AWS allows you by default. So as soon as CPU utilization of the service, and everything is deployed per service, ECS service within the stack, gets above 35%, we'll add another task into the service. And as soon as it gets below 5%, we will remove the task from service. Now remember, there is minimum and maximum. There are three numbers of tasks. It will never scale down below minimum, and it will never scale up above maximum. There are other metrics that are available. I think memory is one, and you can create come up with your own custom metrics for your use case. For our use case, CPU is good enough, and we haven't seen any issues. But if we do, we'll probably look at adding some custom metrics for this. So then it brings me to one before last slide of mine. What's next? So remember, I didn't mention this, but Vanguard is a low-cost investment provider. So for us to get the best optimized expenditure for compute is extremely important. Because right now we're deploying ALB for each one of our stacks, each one of our microservices, ALB is the biggest contributor to the cost. It is necessary for us right now because that's the thing that terminates the TLS coming from outside. It's also the one that has integration with ACM, and therefore we can't really forego it at this point of time, but it's something that you should always keep in your mind if that's the path that you take. There are some alternatives that are available to ALB from routing traffic to the tasks perspective. Remember, tasks are ephemeral, and by themselves, they only have an IP, so you need a way to pass traffic to them. AWS Cloud Map is one such thing. It uses DNS and integration with ECS service also available, and it creates this record with whatever DNS goodies that are available with TTL up to 1 second or as little as 1 second, and it will send traffic with some load balancing capability directly to the task, but it cannot terminate ACM. Cannot terminate TLS. So unless you want to inject certificates directly into your containers and do this operational overhead, having ALB, at least at this point of time, is essential for us. Sizing the task and the memory in the Fargate is extremely important. When you're running in EC2 mode for ECS, you decide what EC2 instances, what are their sizes, and you then can pack your ECS tasks as tightly as possible. That's what you want. That's how you get the best bang for your buck. In Fargate, you need to size each of your tasks individually. So you need to be extremely sensitive. Like, I think you need to default to the very little, very minimal, and then depending on the workload or the application, increase it incrementally just to understand what's the baseline of that application or microservice. Another important thing that I haven't mentioned before, but I think you guys should know, is that it is very important, not always possible, to run in the container applications that as soon as the container starts, the application immediately goes into service. So something written in Go, something written in Node.js, something written in Python. There are other languages out there that are probably more popular than the ones that I just mentioned, such as Java. They have a long instantiation time. And when I'm saying long, it's probably seconds, but tens of seconds, up to a minute, depending how much things you need to do. What happens is the application load balancer, as soon as the task comes up, the Docker container is up, it starts hitting it with health checks. And because we want to be as aggressive as possible so that we can be the most resilient, if Java or any other language which requires long initialization is not yet operational, it will not return to 100. And the application load balancer will mark this container as unhealthy, and you will go into an endless cycle. There's something called a grace period. So for those things that require long initialization time, you need to figure out what your grace period is. We default to 60 because we have a lot of Java. Sometimes it's not enough. We need to change it to 180 seconds, sometimes to 240. But again, my recommendation is, the smaller the Docker image, the faster the application inside a container can go into service and start responding to requests, the more available your entire system is. So I'm saying here smaller Docker image is going to reduce the cost. It will, because the footprint in ACR is less and you're paying by size there. But what we'll do more is make your whole service more scalable. Every event of auto-scaling and self-healing, which is built into our stack, is going to happen that much faster with a smaller container footprint. So we want to experiment with AWS App Mesh. It was announced last reInvent? No, yes, but became GA a couple of months ago, maybe 2 or 3. I don't think it's yet ready for enterprise-grade deployment, but when it does, when it is, and we're doing an active POC with it, together with Cloud Map, it eliminates application load balancer. Now your ECS service can talk to another ECS service entirely over mesh. And hopefully you have MTLS done with ACM, which is not supported yet, but it's like a wish list of the things that you need in order to get to this next-gen architecture. And there is encryption in motion within the mesh itself as well. You can ingest traffic from outside the mesh using ingress and egress gateways. Again, all of those things are on AWS public roadmap for App Mesh, not available yet, but it's something that we want to experiment with, and I think you should as well. And then when you have all those things and ALBs are gone, there is no way for you to do a health check against the container. So Docker released API version 135. I don't know what time frame, but recently, I mean like months, maybe 6 months. That allows you to invoke a shell from outside orchestration inside the container to curl something or run a script. Like I think it's shell or shell CMD. Those are the 2 available API invocations. So then the same health check that you would run all the way through ALB, you would run directly from the API. Now, the advantages of this is you can be a lot more aggressive. The timers there are with milliseconds, not seconds anymore. So you can do 10 milliseconds. And when you do this, your entire system is a lot more elastic. Again, the self-healing or scaling events happen a lot faster, but you need to remember that now you're paying for this with CPU. The more you feed your container, the more CPU you consume from the application perspective. So you need to be extremely sensitive of that. Another thing about health checking that I would point out, and it's not on my slide, is that we always want to create a health check which is extremely elaborate. It goes to dependent services and make sure they're up, or to the database, make sure it is up. When you do it within the context of ECS Fargate, or ECS rather, you need to remember, what is this health check going to do for you? If the container is not healthy, which is what that health check is going to tell you, the only thing that ECS Fargate will do, sorry for touching the microphone, is restart that task. If your backend is not working, restarting the task is not going to help. It's not going to remediate the problem. So create health checks that are simpler than checking everything throughout the entire backend infrastructure, restricted to what's working or not working within the task within the container that is running within your task. So with this, I'm 15 minutes earlier, so giving you the beer time back. Thank you very much for attending, and don't forget to fill your questionnaire. Thank you so much.